Now we must have another way of mm, representing this acceptance angle, that is called the numerical aperture. According to Snell's law, n0 sine theta 1 equal to n1 sine theta 2, where theta 1 is the incident angle, this region is the air medium, this region is the air, so its refractive index is n0, and for the core region we have refractive index of n1, and for cladding it is n2. So Snell's law is telling that n0 sine theta 1 equal to n1 sine theta 2, right? Now if we consider this ABC angle, this angle, this triangle, okay, this triangle, right angle triangle, so phi equal to, this phi equal to, this is 90 degree, this is 90 degree, and this is theta 2, right? So phi equal to pi by 2 minus theta 2, right? Where phi is greater than the critical angle at the core cladding interface. So n0 sine theta 1 equal to n1 cos phi, okay? Or in other words, n0 sine theta 1 equal to n1 into root over of 1 minus sine square phi, cos phi equal to 1 minus sine square phi, sorry, cos square phi equal to 1 minus sine square phi. So using this particular relation. So when the limiting case for total internal reflection is considered, phi becomes equal to the critical angle, right? This phi becomes critical angle for the core cladding interface. Also, in this limiting case, theta 1 becomes the acceptance angles for the fiber, which is written as theta a. So if we combine them, we can write n0 sine theta a equal to n1 square minus n2 square whole to the power 1 by 2. That means square root of n1 square minus n2 square. So this is a very important relationship for optical fiber. And this n0 sine theta a is called the numerical aperture. Okay, so this numerical aperture can be written in as square root of n1 square minus n2 square. So numerical aperture is often used with a fiber in air where n0 is unity. It is simply equal to sine theta a. Okay, when this medium is air, we can assume that n0 equal to 1. So it is basically the sine of the acceptance angles. Okay, numerical aperture is the sine of the acceptance angle. Now, incident meridional ray over the range of 0 to theta a will be propagated within the fiber, that we have already said. That means when the ray is within the acceptance angle, it will be propagated, it will be allowed by the fiber, otherwise it will be lost. The numerical aperture may also be given in terms of the relative refractive index difference, or delta. So we can write it in this way, that delta equal to n1 square minus n2 square divided by twice n1 square, which is very close to uh, approximately, you can write it as n1 minus n2 by n1. Okay, so numerical aperture can also be written as n1 into square root of 2 into delta. So this is another relationship. Instead of writing it in this way, we can write in the similar fashion, we can write the numerical aperture expression in this way. Let us have a problem, numerical problem. A silica optical fiber with a core diameter large enough to be considered by ray theory analysis has a core refractive index of 1.5 and a cladding refractive index of 1.47. Determine the critical angle at the core cladding interface, the numerical aperture of the fiber, the acceptance angle in the air for the fiber. The critical angle phi c at the core cladding interface. So phi c equal to sine inverse of n2 by n1. n2 is given 1.47, n1 is 1.5, so it becomes 78.5 degree. So this is the critical angle. The numerical aperture that we have already discussed, square root of n1 square minus n2 square. So all the values are given, so it becomes 0.3. Numerical aperture is 0.3. The acceptance angle in the air, theta A, it is the sine inverse of numerical aperture. So it becomes 17.4 degree. So you can see that the numerical problems are very easy. Obviously, it is a easy problem, and it is showing how you can use those expressions to solve the problem. Okay. Another problem, a typical relative refractive index difference for an optical fiber designed for long distance transmission is 1%. Estimate the numerical aperture and the solid acceptance angle in air for the fiber when the core index is 1.46. Further calculate the critical angle at the core cladding interface within the fiber. It may be assumed that the concepts of geometric optics hold for the fiber. Actually, what happens when the fiber core becomes very smaller, like few micrometer only, in the lateral direction, hmm, to satisfy the condition of geometrical optics, the lateral extent must be semi-infinite. Okay, but for small core dia, that particular condition, that the in the lateral direction the lateral extent is semi-infinite, is not valid. Okay, under that condition it may happen that we cannot apply the geometric optics, and under that condition we have to solve the Maxwell's wave equation inside the fiber. Okay, but here it is saying that the concept of geometric optics hold for the fiber, right? It is said. So we can calculate the numerical aperture using this particular expression, n1 root over of 2 delta, because index difference is given. Okay, so it is found out to be 0.21. Okay, so acceptance angle can be written in this way. So pi sine square theta A is for small angle of solid acceptance angles in air, that can be written in this way. So it is 0.13 rad. So delta is given in this fashion, that is 1 minus n2 by n1. So n2 by n1 is 0.99. So critical angle can be written as sine inverse of n2 by n1. So it is 81.9 degree. Let us have the concept of skew rays. Actually, when the incident ray is not uh, incident on exactly on the axis, say it incident on this particular point, right? So what happens, it will obviously it will it will follow the similar principle of total internal reflection, right? But since it is not incident on the exactly on the axis, so if we view if we observe the propagation of the light uh, from the cross section, then it will appear as as if it is moving in this way. Okay, it is moving in this way, so it is not exactly going through the axis. It will follow a kind of helical path like this. Okay, with different reflections at different part of the different portion of the core cladding interface. It will move in this helical path, right? So this is what we call the skew ray. Obviously, if we have such skew ray, then the amount of time taken by the wave to travel this length of the fiber will be little bit larger compared to non-skew ray. Get it? Because it has to travel larger optical path. Okay.